So in these examples that are coming up, we're going to be actually using the z-score tables backwards. So let me show you what that looks like with a concrete example. So pumpkins come in all shapes and sizes and weights, and the average weight of a pumpkin in a farmer's field is 4 kilograms with a standard deviation of 0.5 kilograms. So I'm assuming now that that is normally distributed. So as always, my first step is to make a normal distribution curve and label it with the actual values in kilograms and the z-scores. So we've got 4 kilograms here, and it's going to be going up by 0.5 and down by 0.5. You guys are very comfortable, hopefully, by this time doing this. And the standard z-scores are 0, 1, 2, 3, -1, -2, -3. So here's my standard normal curve based on the information given about these pumpkins. Now the farmer knows he will have trouble selling the lighter pumpkins, so he will offer them at a reduced price to minimize his cost. He only wants to reduce the price on 10% of the pumpkins. So we're talking about he wants to reduce the price on the lighter ones, so the bottom 10%. So if I shade that, this will be 10%. So notice in this case, we're given the percentage, but we don't know what the weight is of the pumpkins. That's the unknown part. And that's what the question is. What is the cutoff weight to get this price reduction? So we're going to have to use the Z tables to find the z-score to begin with, because we don't know the pumpkin weight, but we also don't know the z-score. But we can use our standard normal probability tables to figure that out. Now remember, these are the z-scores, this column right here, and everything inside the table, so in other words, everything here are the probabilities of something happening below the z-score, so to the left of the z-score. And we're looking for this percentage to be 10%. And our tables aren't listed as a percent, they're listed as a decimal, so it's 0.10. So I've got to actually find 0.10, or the closest I can, in this table. And it takes a bit of scanning, but if you take a look at this row here, okay, we're getting close to 0.10. So here it's between this number and this number. And so I take the one that's closest, which is this column here. So that is a z-score of -1.28. So this z-score is -1.28. It makes sense that it's negative because it's on the left side of the mean. So that is the right bound, basically, z-score, right side of the shaded area. And now that we have the z-score, we can use our z-score equation, which is z equals x minus mu over sigma, to find the x value, which is measured in this case in kilograms. So the z-score was -1.28 equals the x value, which we don't know, but the average we do know is 4, and the standard deviation was 0.5. So I need to isolate the value of x there, and I'm going to do that by multiplying both sides by 0.5. So that cancels the denominator here, and gives me -0.64 on the left equals x minus 4. And then I'm going to add 4 to both sides to get a value. So I'm running out of room here. X equals -0.64 plus 4, which is going to be equal to 3.36. And I take a look to see if that makes sense on my diagram. So 3.36 that's the weight of the pumpkin, and if I take a look at that, that is matches in here. That's about between 2 and 3.5. So the cutoff weight for the pumpkin is 3.36 kilograms. So he's going to give every pumpkin that is 3.36 kilograms and lower a 10% discount. So let's do this type of problem one more time. This time it's an exam, and it is known that the distribution of marks is normally distributed. So right away I know that I am going to draw my bell curve. Normally distributed, that's what bell curve means. And it has a mean of 51 and a standard deviation of 3.5. So this is my marks as a percentage. And that's 54.5, 58, 61.5. And then going the other way is 47.5, whoops, 44, and 40.5. So this is a pretty low scoring test if the average is 51 and the highest marks are about 62% and the lowest is 40. So this is what happens at lots of times actually at universities where the marks are low and then everything gets scaled. So that's basically what's happening in this question. And so the teacher, the prof, is going to say the top 5% will be an A. So the top 5% means we're looking at the top 5% is on this side. And remember, 5% is going to be looking like this in the table. So in this question, we know that the percentage of the probability of something happening, but we don't know what that cutoff mark is. So this is the part we don't know, which means we're going to be looking at this part of the table to find the closest percentage. Now be careful. Notice that the way the table is set up, it always refers to the area on the left, and we've got it on the right in our original question. So we've actually got to figure out what this percentage is first. Well, the whole distribution is 100%, so this must be 95% or 0.95. So it's 0.95 that I actually have to look up to find the cutoff mark. So I'm going to scan my table again and look as close as I can and find the closest one to 0.95. And it's looks like it's around here, 0.95. It doesn't really matter if you go either way, they're both evenly spaced. So I'm just going to say it's 1.64, a z-score of 1.64. And that kind of makes sense based on what I've drawn in here. That's between 1 and 2. Now the z-score doesn't help us with the mark. We actually have to use the z-score equation to find out what that is. So the z-score is 1.24. The x value is the mark, which we don't know. And we do know the standard deviation is 3.5. So just like in the last one, we're going to have to get x all by itself. So I'm going to multiply both sides by 3.5. And that cancels. And then I'm going to add 51. So it's 3.5 times 1.24 plus 51. And I'm doing that in one step instead of two, like in the last question. And I get a mark of 55.34. And I just double check to make sure that makes sense on my diagram. A mark of 55.3, is that above the average? Yes. So just that simple check will tell you whether or not you're at least on the right ballpark. So the cutoff mark, if we were to round it to the nearest percent, is 55%. So on this test, any student with a 55% or higher is going to get an A. So let's do this one more time. The weight of a 6-month-old baby is normally distributed. clue here is that we're going to do a normal distribution again. And the weight is 7.3 kilograms. And the standard deviation is 0.5. So I'm going to do my 3 ticks. This is measured in kilograms. 3 ticks on the other side. And add 0.5 to each. So this is 7.8. This is 8.3. And this is 8.8. And then going down, we have 6.8, 6.3, and 5.8. And I'm just going to add my z-scores for good measure. And here's my standard normal curve. You are told your baby is in the 80th percentile. So what does that mean? The 80th percentile means that 80% of the babies are below a certain weight and 20% of the babies are above the weight of your baby. So it's basically comparing your baby to everybody else's babies. 80% of them are below and 20% are above. So if I made that, showed that on a diagram, it would, right, 20% would be above and 80% would be below. So now it's just be careful, which of the percentages are we going to look up? We are looking the value to the left of the weight. So that means we're looking up 80% in this case. And 80% is about right here, 0.7995. So that's 0.84. So the z-score is 0.84. That doesn't tell you the weight though, that's just the z-score. So again, we're going to use our formula to figure that out. 0.84 equals the weight minus the average over the standard deviation. And now I'm going to isolate x by multiplying both sides by 0.5 and adding 7.3. I'm going pretty quick through this, but hopefully the repetition makes it a little bit easier. So there's my x value, and if I quickly pick up a calculator and calculate that and double check it on my graph to make sure. So I get 7.72 kilograms. And does that make sense? Yes, that is higher than the average, which is what we're expecting for this value here. It's going to be higher than the average. So that means if your baby is in the 80th percentile, it means 80% of the babies are below your child, which is 7.72 kilograms, and 20% are above.